Hello, we're back. Happy Friday. We're back. I'm going to do another algebra problem because I told myself I'm going to start doing 2 a day. And the first one only took less than 10 minutes. So, we got to keep moving. Problem 4. Let P be a prime. Prove that if every non-trivial finite extension of the field F has degree divisible by P, then every finite field extension of F has a degree, a power of P. Assume characteristic of F equals 0. I don't even want to know what the case is like when the characteristic of F equals P. Like, that's probably just some collapse shit. I don't know. That seems kind of stressful. Okay, so, solution. Okay. Oh, now you get to see this one. Hold on. This is another Haunter line. How your characteristic 0 and U ain't even separable. Now we get to see it. This is what I meant. Now you get to see the application of it. Because over a field, if you have characteristic 0, you have a separable extension, which means you don't have to worry about the roots of the polynomial collapsing because of some weird derivation thing that happens in prime characteristic, where you take a derivative and then you start zeroing out roots of a higher multiplicity. A separable extension means the roots separate. Okay. So let's do contradiction. So suppose K is a non-trivial extension of F with degree which is not a power of P. Okay, now subgroup. I know, you barely see these extensions like this. Hold up. Okay, hold on. Lambda. We're gonna go through it. Okay, so let's see. Let P be a prime. Prove that if every non-trivial finite extension of the field P has degree divisible by P, then every finite field extension of F has a degree of power of P. The fact that they proved this by contradiction is kind of counterintuitive to me because I think a direct proof is maybe actually easier. But, okay. Right. Okay, hold on. So the way that we wrote the proof, you're doing a direct proof, which I think is much easier. They did a proof by contradiction, but I actually think a direct proof is easier. It just depends on how you think about it, really. It's like how your mind sees it. Oh my God. I don't, like, can you just answer me? Sometimes I realize I'm talking to ChatGPT. I think I'm talking to ChatGPT 4.1. I'm talking to ChatGPT 5. And ChatGPT 5 would be like, let me explain a million different steps for shit that you already figured out and just make it longer for no reason. Like, are we not using, come on now. Let's see. So, we can do another one. Okay. let kf be a finite extension, k over f, okay, be a finite extension. Since f has characteristic 0, all extensions are separable. Let L be the normal closure. Okay, sure. Of K over F. Then L over F is finite Galois. By hypothesis, every non-trivial extension of F has degree divisible by P. In particular, L over F is a power of P. That's the multiplicity thing. Let G be the Galois group of L over F. So it has whatever. And H be the Galois group of L over K. Did I write this? It doesn't look as nice. L over K. Why am I writing it? Just feels like I didn't write it right. Over F. Okay. That's just fundamental theorem of Galois theory. Both are P powers. Yeah, that's really it. That's why I don't know why they did the contradiction argument. I mean, it works, but it kind of is like not. Again, it just depends on how you think about it. Because immediately you just look. Like, if you look at the problem, it just falls out immediately if you do it directly. Because you can kind of see. It's like, yeah, we have everything working nicely because we're doing Galois extension. So just multiply. If that one's a power of P, that one's a power of P, blah, 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 blah. Every. Has a degree power of P. Okay. That's the proof. I like this proof better. But it's the same. I mean, this one's just straight up using the fundamental theorem of Galois theory, which could totally do direct is cleaner, yeah. Yeah, direct is cleaner. Hold on, I'm gonna talk to Lambda. Direct is cleaner because it just comes like, it's almost set up for it to be direct. It's like all you have to do, as soon as you pass to the normal closure, you're just stacking towers, and then now you're just arguing, okay, well, if this is a power of P, then that has to be a power of P.
Exactly, you've summed out perfectly. Once you move to the normal closure and use the Tower law, everything slots into place. You're just looking at how the degrees factor through the Galois group and its subgroups. And since every non-trivial extension held a degree divisible by that prime P, you end up forcing the whole chain of extensions to have degrees that are powers of P. So the direct proof is like you said. It's all set up for you to just stack those towers, apply the divisibility condition, and conclude that every degree is indeed a power of P. It's definitely a nice and elegant way to do it.
And so we're using the fundamental theorem of Galois theory to get the correspondence for the Galois group orders, which is going to give us the power of P decomposition.
Exactly, that's the key tool here. We're relying on the fundamental theorem of Galois theory, which sets up a one-to-one correspondence between intermediate field extensions and subgroups of the Galois group. So once we know that the entire Galois group has order that's a power of P, every subgroup's index, and thus every field extension degree that we get from that subgroup chain, is also a power of P. In other words, the fundamental theorem of Galois theory is what lets us decompose the extension degrees into these subgroup indices, and since the whole group is a P group, all those indices are power of P as well. So yes, that's exactly what we're doing, using the Galois correspondence to show that the degrees must break down into powers of P.
So the key theorem. Fundamental theorem of Galois theory. And there you go.